The demonstration that's up next is Hunk-a Burnin Ice. It's a favorite demonstration because it produces a lot of excitement. It's a very visually stunning experiment, and it can be used at a couple of different places in your curriculum. So let me show you what I've got set up first, and then we'll do the demonstration and talk about the application. I'm starting with 2 chunks of dry ice, and it's important that the 2 chunks of dry ice are flat surfaces so that they will fit snugly together. And as you can see, these are relatively flat surfaces, nice and smooth so that they will mate well together when we get ready to use them. Into one of the blocks, I have taken and carved out a small depression using a metal scoop so that I have carved into the dry ice, and I've made a depression that's about the size of a silver dollar, perhaps, and perhaps a little deeper than that. And I did that just by scooping this around so that we could get a depression inside of here. What we will do is to place this behind a shield because of the sparks that will be generated. And we'll place a small amount of magnesium turnings into that. I'm estimating that I'm using about 5 grams of magnesium turnings for that. And then we will light that with a propane torch. And sometimes it's a little difficult to get that going. I don't recommend that you put your magnesium turnings into the dry ice until immediately before you get ready to light it. Because if you put it in too early, the magnesium turnings, obviously, with the very low heat capacity, will chill quickly, and it will be hard to get those to ignite. So we'll put those in right ahead of the starting point. Then we will light the magnesium turnings, and I'll immediately invert the other block of dry ice on top to capture that, so that we have the magnesium reacting between the 2 blocks of dry ice inside of there. I would caution you that this produces some amount of smoke, so you will want to do this in a well-ventilated area. And it also produces, in addition to the visible light, some amount of ultraviolet light. So you probably should take some precautions in terms of making sure that students would not look directly at that. Goggles will help screen the ultraviolet light, and so those would be good things to work with as well in order to protect the students. I'm going to pre-light my burner so that it's ready to go, again, so that I don't have the magnesium in for a long period of time before the reaction starts. We're going to make sure that we have all flammable materials away from this. I'm filling the depression with the magnesium turnings, and I'd estimate that there would be around 5 grams or so of magnesium. We'll light it, and then after we've got that lit, we will dim the lights, and we'll watch the reaction take place. The reaction can be tricky to ignite. We've got it going. And the purge fan. Notice the nice afterglow that we're getting. The reaction is still continuing to burn even though the major part of that reaction process is stopped. And that's a lot of heat. The magnesium is very, very hot inside of there as it was working and reacting. I'll take the shield down so that we can see a little more clearly what we have taking place. Perhaps you can note that there is a burn spot in the top of the dry ice where the heat from the reaction was taking place. And we'll take a look at this interesting piece of stuff, this product, this reaction that we have in here. It's relatively fragile, but let me pop it out. And then see if I can hold that up for you. So we have this piece that is whitish, grayish on the outside, but yet if I take that and I break it open, what I see on the inside, let me break that just a little larger, is pure black. So I like to call it a reverse Oreo cookie because we have the white on the outside and the black in the middle. Now, what is the chemical reaction that was taking place with that? The reaction that we have here on the board shows that we started with magnesium and we immersed that into a carbon dioxide environment by trapping it between the blocks of dry ice. That produced magnesium oxide, which was the grayish or the whitish color that we saw on the outside of the little cookie that we had formed, and pure carbon was trapped into the middle of that process. If we also take a look at the depression that we started with, as you could expect, that depression is quite a bit deeper than what we began with. You can use this block of ice, because I know that for many people, dry ice is difficult to come by, and it is somewhat expensive. You can use this block of dry ice a couple of times, but you have to be very careful that you don't exceed the thickness of the dry ice, and the magnesium would then end up burning outside of that. And so sometimes what I've done is that use the bottom block maybe once or twice for the demonstration, and then carve a hole into the top block, and then use it for the bottom a couple of times over. And that way, out of $10 worth of dry ice or so that I would have bought, I would have several different times that I could run that demonstration. So because of the difficulty and the expense of getting dry ice for some people. Where would I use this reaction, and what is the teaching value in it? Well, for one, it's just sheer fun. It's a good demonstration if you're doing like a Halloween show or a whiz-bang show of some type or other, where you want to just show some fun of chemistry. So perhaps you're doing an elementary science show or something of that type. But you must always make sure that if you're doing that the environment is safe, that you have the ventilation that you're going to need, and that you have the ability to control the reaction that's taking place. The reaction also works very nicely because it is an oxidation-reduction reaction that's taking place that we have here. So we're going from magnesium with a 0 oxidation state to a magnesium 2+ oxidation state here. Here's an example of a redox reaction, and so that makes a very nice part. If you're doing redox, there's a demonstration that you could do that's rather spectacular and would make that happen. This is also a nice reaction when you're talking about types of reactions, single replacement, double replacement, those types of things, to take a look at this process because, again, it is a type of single replacement reaction. You start off with your magnesium and you end up with carbon as a single element there. And so that's kind of a different way that you could work with the reaction. And I've also used this when talking about combustion. And the fact that combustion, we talk about that being a reaction in the presence of oxygen, but many times students have the misconception and they believe that reactions or burning can only occur in the presence of oxygen. Well, true combustion, of course, does, but we saw very clearly that there was something burning inside those blocks of dry ice, and that nonetheless is a type of combustion. They believe that nothing can react in the presence of carbon dioxide. That's why we use it for a fire extinguisher. And yet we see very clearly that there are reactions that can take place in that environment. And so that's kind of a nice safety issue that you can talk about, that you would want to make sure that in certain situations that you had the proper fire extinguisher. While many times you might have a carbon dioxide fire extinguisher present, it wouldn't be appropriate if you were working with reactive metals, for example, such as magnesium, because they can continue to react once they have started. So that's the Hunk-a Burnin ice. I'll let you do the singing part out on your own, but it's a fun demonstration and it's one that produces a lot of wow factor, but there's good solid science and chemistry behind it, and that's why we like to use those things, is because it captures the imagination as well as teaching a really good chemistry concept.